Good morning, students. Today, I am going to discuss about the Maxwell's equations. Maxwell's Maxwell's equation. Maxwell's equation or Maxwell's relations. Maxwell's equations. This equation is very much helpful in replacing non-measurable properties in thermodynamic equations by means of measurable properties. In thermodynamic equations, the non-measurable properties are replaced by measurable properties by using Maxwell's equation. Hence, this knowledge is very much essential. The Maxwell's equations or relations are very much helpful in estimation of changes in entropy by using pressure, volume, temperature. Changes in entropy by using pressure, volume, temperature. Maxwell's equations are the relations are derived from fundamental property relations. The first fundamental property relation, changes in internal energy is equal to Tds minus Pdv, and we know that each energy property has a set of canonical variables. For internal energy, it is function of entropy and volume. Now I am going to find the total differentiation from canonical variables. From this equation, total changes in internal energy is equal to changes with respect to entropy at constant volume plus changes with respect to volume at constant entropy. Clear? Now I am going to write this equation: dou U by dou S at constant volume into ds plus changes with respect to volume dou U by dou V at constant entropy into dV. See this equation: total changes in internal energy is equal to T ds. So ds are common. Hence I am going to write dou U by dou S at constant volume is equal to T. Similarly, dou V and dou V are same. Dou U by dou V at constant entropy is equal to P minus P. Okay. Second differentiation with respect to V at constant entropy. So dou square U divided by dou S dou V is equal to dou T divided by dou V at constant entropy. Clear? Next, second differentiation with respect to S at constant volume. So dou square U divided by dou V dou S is equal to, with respect to S at constant volume, minus of dou P divided by dou S at constant volume. See this: dou square U by dou S dou V. Dou square U by dou S dou V, both are same. Hence I am going to write dou T, this one, by dou V at constant entropy is equal to dou P by dou S at constant V minus tau. This is the first Maxwell's equation. Next, second Maxwell equation for enthalpy. We know the fundamental property equation for enthalpy: dH is equal to TdS plus VdP, and enthalpy H is the function of the canonical variables entropy and pressure. Now I am going to differentiation with respect to S at constant P plus with respect to P at constant S. Hence the total differentiation dH is equal to dou H by dou S at constant P into ds plus with respect to P at constant entropy. So dou H divided by dou P at constant entropy into dP. See this equation, changes in entropy, changes in entropy. Hence, dou H by dou S at constant P is equal to T. Dou H by dou S at constant P is equal to T. Similarly, dou H by dou P, dou H by dou P at constant S is equal to V. Here, second differentiation with respect to P at constant entropy. Therefore, dou square H divided by dou S dou P is equal to with respect to P at constant entropy. Hence, dou T divided by dou P at constant entropy. In this equation, second differentiation with respect to S at constant pressure. So, dou square H divided by dou P dou S is equal to with respect to entropy at constant pressure. So, dou V divided by dou S at constant pressure. Therefore, both are same. Dou square H divided by dou S dou P, dou square H divided by dou S dou P. Hence, these two are same. Now I am going to write dou T by dou P at constant entropy is equal to dou V divided by dou S at constant pressure. This is the second Maxwell relation. Third, thermal free energy or work function. dA is equal to changes in thermal free energy is equal to minus P dV minus S into dt. We know that thermal free energy, the canonical variables are function of volume and temperature. Now I am going to differentiation with respect to volume and constant temperature plus with respect to temperature at constant volume. The total differentiation dA is equal to dou A divided by dou V at constant temperature into dV. At constant temperature into dV plus dou A divided by dou T at constant volume into dt. Now dV, hence dou A by dou V at constant T is equal to minus P. Dou A divided by dou V at constant P is equal to minus P. Similarly, dou A by dou T at constant volume is equal to minus L. Clear? Second differentiation with respect to T at constant volume. So dou square A divided by dou V dou T is equal to minus of dou P divided by dou T at constant volume. Second differentiation with respect to volume at constant temperature. So dou square A divided by dou T dou V is equal to minus of dou S divided by dou V into constant T. Listen, dou square A divided by dou V dou T. Dou square A divided by dou V dou T. Both are same. Hence, I am going to write like this: minus of dou P divided by dou T at constant volume is equal to minus of dou S divided by dou V into constant temperature. This is the third Maxwell's relation. Fourth, Gibbs free energy. Fourth, Gibbs free energy. dg is equal to v dp minus s into dt. And Gibbs free energy G is the function of pressure and volume. Pressure and temperature. Pressure and temperature are the canonical variables or special variables for Gibbs free energy. Gibbs free energy depends on the canonical variables of pressure and volume. Now I am going to get total differentiation first with respect to pressure at constant temperature plus with respect to temperature and constant pressure. So the total differentiation to dg is equal to dou g divided by dou p at constant temperature into dp plus dou g divided by dou t at constant pressure into dp. dp, hence dg by dp at constant temperature is equal to v. Dou g divided by dou p at constant temperature is equal to v, volume. Similarly, dou g by dou t at constant pressure is equal to entropy. Dou g divided by dou t at constant pressure is equal to minus s. Now second differentiation with respect to temperature at constant pressure. So dou square g divided by dou t is equal to, with respect to t at constant pressure, so dou v by dou t at constant pressure. Similarly, second differentiation with respect to p at constant temperature, dou square g divided by dou t is equal to, with respect to p at constant temperature, minus of dou s by dou p at constant temperature. See, dou square g divided by dou p dou t, dou square g divided by dou p, both are same. Hence, I am going to write like this: dou v by dou t at constant pressure is equal to minus of dou s divided by dou p into constant temperature. This is the fourth Maxwell relation. Clear? Simple closed system under reversible condition. Maxwell's relations are very much essential in estimation of changes in entropy by knowing pressure, volume, and temperature. Many of the thermodynamic equations are there. It has non-measurable properties. Once you have the knowledge of Maxwell's relation, this knowledge will be helpful to replace the non-measurable properties in thermodynamics equations by using measurable properties. Thank you. This essentially is very much important. Thank you, students.